This is the group work that goes along with section 4.4, conditional probability. This is definitely a difficult topic, just theoretically understanding what it means to be a conditional probability. So I recommend that you look through the examples from the lecture and make sure you familiarize yourself with the different ways this can be presented before you try the group work. Within the group work, we start out with this situation where a student's going to take 2 buses to get to campus. The first bus is on time 90% of the time. The second bus is on time 80% of the time. The first question that's asked about this situation is, if they are independent events, what's the chance that the student is on time because both buses are on time? If they're independent, that means one bus being on time doesn't impact what I think about the second bus being on time. This doesn't really make sense in the real world because a lot of the reasons why a bus would be late would affect both buses equally. Things like weather, things like traffic from a big event happening nearby, things where the reason a bus would get off schedule would probably impact multiple other buses on the same day. So this idea that they wouldn't move in the same direction, that they'd be completely separate from each other, doesn't really hold in the real world, but we're going to look at it that way the first time. So we're going to say, if we're looking for 2 things, the probability of them both happening at once when they're independent, I just take the first probability, multiply it by the second probability. As a decimal, the probability that the first bus is going to be on time, since it was 90%, to get it as a decimal, I just take whatever it is as a percent, divide by 100. 90 divided by 100 would give me 0.9. The same way, if I took 80% divided by 100, I get the probability that the second bus is on time is 80 divided by 100 is 0.8. To get their intersection, or the chance that they both happen at the same time, again, our multiplication formula for independent events is that the probability of first intersect second, meaning both buses are on time the same day, is the probability of the first bus being on time, 0.9, times the probability of the second bus being on time, 0.8. When I multiply those 2 things together, I get a final answer of 0.72. So if these were completely independent, the 2 buses, it would be 72% of the time that the student arrived on time to class. In reality, they're not independent. So when things aren't independent, we need to use a different formula than just simply multiplying. The formula that we really end up using is a conditional formula. So when we have a conditional formula, we need to know which of the 2 things has already happened and put that after the given line to say it's already occurred. So it's important to read kind of the way this is written. If I read directly from the group worksheet, it says, if the 2 buses are not independent and they're both on time 75% of the time, what's the conditional probability that the second bus is on time given that the first bus was on time? The important thing is recognizing what comes after that word given. What do we know already occurred? So in this case, it's given the first bus already was on time. What's the probability the second bus is also on time? When we're setting one of these up, after the given line is first bus, this we know already happened. Before the given line is second bus, that's what we're trying to see what the chance of it happening is. Our general formula is we're looking for P of A given B. If we do that on top, we get P of A intersect B, so the probability of both things happening. And on bottom, we get the probability of whichever one is after the given line. In this setup that I originally did, it was A given B, so probability of B is on bottom. If we apply that to the way I've set up second given first, this probability, P of second given first, has to equal, as a numerator, the probability of them both happening together. Well, we were told that was 75%. If I take 75% and divide by 100, that's how I get the decimal, 0.75. What's after the given line is first, so I go back to find the probability of the first thing happening. Since the probability of the first thing happening is 0.9, I put 0.9 on the bottom. Into my calculator, I divide 0.75 divided by 0.9, and that's how I get to my final answer here, which I got to be 0.83. The probability that the second bus is also on time Given that the first bus was on time, we expect it to be on time 83% of the time. Slightly more than the 80% that we expect if we don't know anything else about the world. So once you tell me the first bus was on time, it increases the chance that I think the second bus will also be on time. In problem 3, we have the same general idea. We're told what both of them are, but then we're asked instead, what is the conditional probability that the first bus is on time given that the second bus was on time? So in this case, after the given line, I put second bus because that's the one we know already happened. If we know the second bus has already occurred and we're trying to find the probability of the first bus occurring, what we're really going to do is take the probability of both happening, probability of first and second, and divide it by the one we know already happened. After the given line in this case is probability of second. Both happening was given to me as 75% or 0.75, but this time instead of dividing by 0.9, which was the probability of the first being on time, we're going to divide by 0.8, the probability of the second one being on time. Again, the reason that we're doing this is because it's the one that comes after the given line. It's the one that we know already happened. It already happened that the second was on time, so it's out of those 80% of the times, out of all the things where the second's on time, we know that 75% of all the times the first is also on time with it. So now if we take that 0.75 in the numerator, divide by 0.8 in the denominator, we get to the conditional probability, which I get is 0.9375. Absolutely fine if you rounded this up to 0.94. I'm just showing the unrounded version here. In WebAssign, it'll usually tell me how many decimal places I want to round to. If it doesn't, it means it wants it unrounded. All right. The next way that we're presenting this after using this formula is we're looking at it within the two-way tables. So we looked at two-way tables the class before where we just tried to find what row totals, column totals were, found unions, intersections, and the complement. Now we're doing work with the conditionals. The way that the conditionals are going to work is it's really going to isolate a row or column, but I still need all my column totals and row totals before I can start isolating them. So I'm going to go one by one and total up the columns. 9 plus 1 gives me 10 total people living on campus. 7 plus 3 gives me 10 total people driving to campus. And 5 plus 5 gives me 10 total people taking the bus. On time, 9 plus 7 is 16, plus 5 is 21. 1 plus 3 is 4, plus 5 is 9. Whether I add 10, 10, and 10, or 21 and 9, I get to the table total of 30 total people. When I'm asked, what's the probability somebody lives on campus given that they're on time? I always want to start with what comes after the given line and see that as isolating either a column or row. In number 4, after the given line is that we're on time. On time is this first row. So basically, unlike all the other fractions that we would set up, where we'd look at the table total as the denominator and say it's out of everything that could happen, when we have a conditional, the denominator changes. It's only out of the row or column that we're isolating. So in this case, where we're trying to find the probability that they live on campus given that they're on time, we're isolating the row on time, so we're only dealing with these 21 things that happen in the top row. For that reason, my denominator is 21. We know the person was on time. Now that we know the person was on time, what's the chance that they lived on campus? Live on campus is 9 within this row that we've isolated. We're not looking below in the people who were late because we already know the person wasn't late. We've conditioned it on them being on time. So we isolate this row for both the total that goes in the denominator and we look to the intersection of what comes before the given line. Here, the intersection of live on campus with on time is that single cell 9. 9 over 21 can really be reduced by 3 to get 3/7. For number 5, it asks what's the probability that they live on campus given that they're late. This time we're isolating the second row, the row late. Within this row, 9 is the row total, which becomes my denominator. I then look for the column overlap from what's in front of the given line. Live on campus is this first column. Where that intersects the row late that we've isolated is in this single number 1. So my final answer for the probability that they live on campus given that they were late is 1/9. This can be read as what's the probability that somebody is on time given that they live on campus. So here we've isolated a column instead of isolating a row. We start out by saying what's the column total? People who live on campus is out of 10. So I make this out of 10. Within this column, we're now looking what fits in front of the given line, people being on time. Within this column, the ones that are on time are these 9. So if I know they live on campus, there's a 9/10 chance that they're going to be on time. Over here, we're doing now, what's the probability somebody's on time if I know that they're driving to campus? So again, after the given line is a column, specifically drive to campus, we start by isolating this column. Within this column, there's a total of 10 things that can happen. Of those 10 things that can happen, the ones that fit with on time, this top row, are the 7 here. So 7 of the 10 students who drive to campus are on time. The probability that somebody's on time given that they take the bus, again, I'm isolating what comes after the given line, so I'm isolating the column, take the bus. Within the take the bus column, there's 10 total items. Of them, the ones that are on time is what intersects this top row. Right there is where students are on time and take the bus. 5 out of the total 10 in the in the column that we isolate. For 9 and 10, we're conditioning things. For 9, we're conditioning something on them being late, we're conditioning it on, we know that they were late. What's the probability that they took the bus? So late comes after the given line. Late is a row. We know we're in this row that's out of 9 total people. Of those 9 people that were late, 5 take the bus. So 5 out of 9 is my final fraction. Sorry, I was talking a lot there. For problem number 10, this is a trick. This is basically to reinforce this idea of things being mutually exclusive. In this case, it says what's the probability that they live on campus or that they take the bus given that they live on campus. Well, given that they live on campus would be this first column. Within this first column, nobody takes the bus. If they live on campus, they're walking across campus to get to their classroom. So if I condition one column on another, there's nothing that can exist in both these columns at once. Since they're mutually exclusive, meaning they must belong to one or the other, they can't belong to both at the same time. When I condition one on the other, it occurs with probability 0. There's no items that are both live on campus and take the bus. In the second half of 4.4, we have a situation where we have 20 equally likely events. I've written out the entire sample space here, just basically showing E1 through E20 is everything that can possibly happen. We then have 4 defined events, event A, B, C, and D. Event A, has E1, then E11, 12 through 19. Event B has E1, E6, E11, E16. Event C has all the even numbers, and event D has all the multiples of 3. Next to each of them, we've written what the probability of them are. Basically, each time we're taking how many individual events fit into A. So here we have 10 possible outcomes. We take that out of how many total possible outcomes are in the sample space, which is 20. 10 out of 20 is where I'm getting that 0.5. 4 out of 20 is where I'm getting that 0.2. 10 out of 20 again is 0.5. And here 6 out of 20 is 0.3. The same way that we did that, where we said how many events fit this thing, and then use that out of the total of 20 to determine the probability, we're going to use various formulas and various ways of looking at it, but really it boils down to, for any of these questions, we're looking at how many events fit out of how many are in the sample space. So the first thing that we're asked is what's the probability of A complement? I could write out the set of A complement by going through and saying, well, E1 is already an A, so we're not going to count it, but E2 isn't, E3, E4, E5, E6. I could list them, E2, E3, E4, and so on until I had everything that was in the sample space that was not in A. I could then add up how many there are, divide by 20, and that would give me the correct answer for A complement. But there's an easier way. My complement rule says if I know what P of A is, to find P of A complement, just do 1 minus what I know P of A to be. Since I know P of A to be 0.5, P of A complement equals 1 minus 0.5, or just 0.5. I assure you that if I'd written all these out, there'd be a total of 10 things that were not in A but were in the sample space, and that 10 over 20 would also get me to the same 0.5. But it's easier to see using the complement rule, so when I go to do 12 D complement, instead of adding up all the things that aren't here, I'm going to say if the probability of D is 0.3, we're going to do 1 minus 0.3 to get the final answer of 0.7. For the intersection, I am going to want to write out what fits. So on the test, I think these are 3 points each. I do recommend that you tell me what fits into the set so that if you accidentally just miss one, I can circle it and take 1 point off instead of taking all the points off if you just give me a probability that doesn't line up with what's on my key. So when I'm doing A intersect C, I'm looking at set A and set C and saying, what's the same? E1's not in C, E11's not in C, E12 is. That's the first thing that's in the intersection set. As I move across, E13's not here, but E14 is. E15's not, but E16 is. E17's not, but E18 is. E19's not, so as we read across everything that was in A, we found a total of 1, 2, 3, 4 things that also appeared in C. That means their intersection has 4 events in it. Out of the 20 total, 4 out of 20 is 1/5, or 0.2 when I put it in my calculator. When I go to do B intersect D, I'm looking for things that are both here and here. E1 is not in set D, E6 is, so I'm going to put that in their intersection. E6, E11 is not here, E16 is not here. So of the 4 things in B, only one of them, E6, also appeared in D. That's the only thing in their intersection set. So there's only 1 out of 20 possible things that's in both B and D at the same time. 1 out of 20 is really 0.05 as a decimal. When I go to do a union, here I have to include anything that's in set A, as well as anything that's in set B, without double counting anything that's in both. So I'm going to try and read across in order of the sample space. They both have E1, so I'm going to start out by putting E1 in. Only once, not twice, because I don't want to double count it. The next lowest thing that I see in both A and B is this E6. Then I see E11 in both sets. Again, I don't want to double count it. From there, set A counts all the way up to 19. So everything from 11 to 19 is going to be in there. 16, I'm not going to double count. So I'm just going to start from this 11 that I have and keep going with E12, E13, E14, E15, E16, E17, E18, and finally E19. Notice that set A doesn't have E20. It's easy to think that you're going to the end of the sample space, but you're not. You're stopping there at 19. Again, I do know that set B also had this E16, but we don't need to double count it. So we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Out of the 20 total, which as a decimal would be 0.55. When we go to do C union D, same idea, start at the lowest event number that you see in either set. E2 I'm going to include. The next lowest I see is E3. I don't double count it. E4, I'm sorry, it's only in set D. E4 I see. I don't see E5. So I skip E5, sorry. I do see E4, I don't see E5, so I go to E6. Again, I'm not counting it twice, I'm only counting it once, even though it occurs in both sets. Then I see 8, 9, 10, 12, E8, E9, E10, E12. After 12, the next one I see is 14, then 15, then 16, E14, E15, E16. Then I see E18 in both sets. And finally, E20 from set C. As I go to count how many things count in C union D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 things. 13 out of the total 20 available gives me a decimal of 0.65. When I go to do these two complements, these look like really tricky problems. This is asking me to do an intersection, then do a complement. This is asking me to do a union, then do a complement. But for both of these, as it will happen on the test, I already have done the intersection or union on the inside in a previous problem. I just need to use my complement rule, 1 minus the answer I got in the previous problem, to get to my final answer here. So the probability that something is A intersects C's complement, I'm going to find by looking down at what I got for A intersects C, which was 0.2, and saying if I take that 1 minus 0.2, it'll leave me with 0.8, all the outcomes that aren't in the set A intersects C. Specifically, since A intersects C, we found to have E12, E14, E16, E18. This would be E1 through 11, 13, 15, 17, 19, and 20. So it would be a total of 16 different things that fit into not A intersects C. If I go to do C union D complement, that's the most recent one we did that we got to be 0.65. So I'm just doing 1 minus that 0.65. When I do that, I get a final answer of 0.35. All of these previous questions were all out of everything that could happen in the sample space. That's why the denominator was 20 each time. The rest of these questions are all dealing with conditionals, where essentially what comes after the given line now redefines the sample space. So when I have a conditional probability where I have a given line and then something after it, instead of being out of 20, the new denominator is however many things fit into the set that's after the given line. So in problem 19, when it says what's the probability of B given A, we start by looking at set A, saying how many things are there, and that creates my denominator. There's 10 total outcomes here in set A, so I'm going to make this out of 10. I now need to know of these 10 outcomes, how many are also in B? Well, E1, E11, and E16 are also in B, so 3 of the 10 total outcomes. This would be 0.3 as a decimal. When I'm asked D given C, I start by looking after the given line is C and counting how many things are in C. There's 10 total things here. That's why this denominator is also 10. I look and see at what the overlap is. E6, that's 1. E12, that's 2. E18, that's 3. So again, it's 3 out of 10, or 0.3. When I do A given D, I start at D and say there's 6 total things in D. So my denominator is 6. Of them, the things that are also in A are E12, E15, and E18. So these 3 things also appear in A. That's 3 out of 6, or 0.5. When I do A given B, B is after the given line. There's 4 total things in B, so my denominator becomes 4. We previously did B given A and said there was an overlap of 3. That overlap hasn't changed. The only thing that's changed is because we conditioned it on knowing B already happened, it's a higher probability that A's also happened. because if B already happened, it's one of these four things, and 1, 2, 3 of them all happen within A. So that's why this is 0.75. Probability of C given D, we're conditioned on D already happening. There's 6 things in D, so it's out of 6. C matching with D includes E6, 1 thing, E12, 2 things, E18, 3 things. So C given D is 3 out of 6, or 0.5. When we're finding the probability that D occurs, given that we already know A occurred, here if we already know A occurred, our denominator becomes out of 10. Of these 10 things that are happening in A, the ones that are also happening in D are this E12, E15, and E18. So 3 of the 10 things, or 0.3. The last one, number 25, is kind of a trick. It says, what's the probability that event C occurred if we already know event C occurred? So if I was setting this up the same way I did the previous ones, I'd condition it on how many things are in set C. There's 10 things. Of them, all 10 overlap with C. Whenever you have something conditioned on itself, it's like saying, if you know for a fact this thing happened, what's the chance it happened? 100%. This is always going to reduce to as a decimal 1, which we know represents as a probability 100% of the time. If I condition something on itself, we already know this event occurred. What's the chance it occurred? 100%.